Our next lecture is nuclear radiation. The synopsis of this chapter will introduce you to the introduction of nuclear chemistry, natural radioactivity, radiation measurement, medical applications using radioactivity, and a special topic on the connection between chemistry with environment and health. There are 7 topics that will be discussed, which are: Introduction, Natural radioactivity, Nuclear equations, Radiation measurement, Medical applications using radioactivity, as well as chemistry, health, and environment. Without further delay, let's start with an introduction for this chapter. The history of nuclear radiation was started since 1934, and was established thereafter. In 1937, first radioactive was used to treat a patient with leukemia. Then, in 1946, radioactive iodine isotope was used to diagnose thyroid function and cancer. In 1980s, a variety of radioactive substances were used to produce image of an organ, such as liver, thyroid gland, kidney, brain, and to detect heart disease. Today, nuclear medicine provides information about the function and structure of every organ in the body, which allows the nuclear physician to diagnose and treat disease early. Next, we move to the natural radioactivity. When we talked about natural, it means naturally occurring radioactivity. Do you still remember our lecture on atom and electron? Stable atom has 8 valence electrons in its outer shell. An isotope is more than one atom, which having different mass. Most naturally occurring isotopes of elements up to 19 have stable nuclei. At higher atomic number, from 20 to 83, usually have one or more isotopes that have unstable isotope. Unstable means that there are so many protons and neutrons are crowded in their atom, and strong repulsions between them makes those atom unstable. When a nucleus is unstable, it is now called radioactive, which means that it will spontaneously emit energy to become more stable. This energy called radiation. Radiation is produced in the form of particles, which are alpha, beta, and gamma. Next, we move to the types of radiation. The release of radiation of any type produces a more stable and lower energy nucleus. One type of radiation consists of alpha particles. Alpha particle contains 2 protons and 2 neutrons, which gives a mass number of 4, an atomic number of 2. Because it has 2 protons, alpha has a +2 charge. Or we called it helium nucleus. Another type of radiation occurs when a radioisotope emits beta particles. Beta particle is a high-energy electron, has a charge of -1. Due to its masses is less than proton, so a mass number is 0. It is represented by Greek letter, beta, or symbol of electron, with the charge -1. Next is positron. It is similar to an electron, except that a positron has a positive charge. The last type of radiation is gamma rays. Gamma rays are high-energy radiation, an unstable nucleus. Because gamma rays are energy only, there is no mass or charge associated with their symbol. Next, we move to how to protect ourselves from nuclear radiation. Nucleus radiation is harmful because the particles emitted tremendous energy. Therefore, it is important for us to prevent exposure with a proper shielding. Alpha particle, for example, is the heaviest particles. A piece of paper, cloths, and our skin are protection against alpha particles. Lab coats and gloves will also provide sufficient shielding. However, it can bring serious internal damage, because it causes high ionization in a short distance. Next, beta particles have a very small mass, and move much faster and farther than alpha particles. They can pass through paper, and can penetrate as far as 4 to 5 millimeters into body tissues. External exposure can burn the skin, but they are stopped before they can reach the internal organs. Heavy clothing such as lab coats and gloves are needed to protect the skin from beta particles. The last one is gamma rays. It has great distance through the air, and much materials, such as body tissues. Only dense shielding can stop them, such as lead or concrete. Because they can penetrate so deeply. Exposure to gamma rays can be extremely hazardous. Even the syringe, used to give an injection of gamma-emitted radioactive isotope, is placed inside a special lead glass cover. So, try to minimize your time in a radioactive area. Why? Because a certain amount of radiation is emitted every minute. Keep your distance. The greater the distance from the radioactive source, the lower the intensity of radiation received. Next, we move to the nuclear equations. When a nucleus spontaneously breaks down, by emitting radiation, it is called radioactive decay. Or in a simplest sense, is a splitting of radiation to a stable form. It can be shown as a nuclear radiation. This equation shows a general nuclear equation of radioactive decays. Let's start with an alpha decay. Alpha emitters are radioisotopes that decay by emitting alpha particles. For example, uranium-238 decays to thorium-234 by emitting an alpha particle. So, uranium is called alpha emitters. As shown in this figure, it clearly describes the splitting of uranium to the most stable atom of thorium, an alpha particle. Next, we move to the beta emitters. In beta emission, the unstable nucleus converts a neutron into a proton and a beta particle. For example, carbon-14 decays by emitting a beta particle and forming a nitrogen nucleus. This figure shows how carbon as beta emitter splits to beta particle and nitrogen atom, which is more stable. Next, the other two emitters are positron and gamma emitter. In positron emitter, a proton in the nucleus is converted to a neutron and a positron, which leaves the nucleus. While gamma emitters are very few, although gamma radiation accompanies most alpha and beta radiation. In radiology, one of the most commonly used gamma emitters is technetium. By emitting energy in the form of gamma rays, the nucleus becomes more stable. This figure summarizes the changes in the nucleus for alpha, beta, positron, and gamma radiation. Next, we learn on how to produce radioactive isotopes. Today, there are more than 1,500 radioisotopes are produced by converting stable, non-radioactive isotope into radioactive ones. The process of conversion of stable isotope into radioactive is called transmutation. To do this, a stable atom is bombarded by fast-moving alpha particles, protons, or neutrons. When stable nucleus absorbed these particles, the atom is now a radioactive isotope, or radioisotope. In this bombardment reaction, a neutron is emitted, such as in this example. In the next topic, we will learn on how to measure the radiation. One of the most common instruments for detecting beta and gamma radiation is the Geiger counter. It consists of metal tube filled with a gas such as argon. Radiation is measured in several different ways. We can measure the activity of the radioactive sample, or the impact of radioactive on biological tissue. The activity is measured in terms of the number of nuclear disintegrations per second. The unit is in curie, equal to 3.7 times 10 to the power of 10 disintegrations per second. Curie was named for Marie Curie, that discovered the radioactive elements. The SI unit of radioactivity is becquerel, BQ, which is 1 disintegration per second. After we measure the activity of a radioisotope, we often want to know how much radiation are the tissues in the body absorb. The rad, radiation absorbed dose, is a unit that measures the amount of radiation absorbed by a gram of material, such as body tissue. Rem, radiation equivalent in human, measures the biological effects of different kinds of radiation. For example, alpha particles don't penetrate the skin. But, if they enter the body by some other route, they cause a lot of damage. High-energy radiation, such as beta, that penetrate the skin and travel into tissue, cause more damage. Gamma can cause great damage due to high ionization. SI unit, which equivalents to 100 rem, is the sievert. Next, we learn on background radiation. We all exposed to low levels of radiation every day. Naturally occurring radioactive isotopes are part of the atoms of wood, brick, and concrete in our homes and buildings where we work. This radioactive is called background radiation. It is present in soil, food, water, and air. For example, one of the natural occurring isotopes of potassium-40, and present in any potassium-containing food. Cosmic ray is produced in space by the sun. People living at high altitudes receive more radiation from cosmic rays than those who live at sea level. We also receive radiation from television, in a medical clinic, dental, and chest X-rays. Next is radiation sickness. The larger the dose of radiation received, the greater the effect on the body. For example, if you received less than 25 rem, this usually cannot be detected. However, at 100 rem, it will decrease the number of white blood cells, which is important to protect our body from disease. If you received more than 100 rem, you will suffer with radiation sickness, such as nausea, vomiting, fatigue, and a reduction in white cell count. More than 300 rem, it can lower the white cell count to 0, means that no any protection in our body. And, if you received 500 rem, it is expected to cause death in 50% of the people receiving that dose. This amount of radiation is called the lethal dose, for 1/2 the population, LD50. Radiation dosage of 600 rem causes fatal to all human, within in a few weeks. As I said before, radioactive was first applied in medicine, to treat diseases. Now, we will learn on what are the medical applications, using radioactivity. When a radiologist want to determine the condition of an organ in the body, the patient is given a radioisotope that is known to concentrate in the organ. So, radioactivity is used to determine the condition of an organ in the body. Body can't differentiate between a non-radioactive and radioactive one. However, radioactive atoms can be detected because they emit radiation. So, after a patient receives a radioactive, a scanner is used to produce an image of the organ. Some radioisotopes used in nuclear medicine are listed in this table. A common method of determining thyroid function is radioactive iodine uptake, RAIU. Taken orally, radioisotope of iodine-131 mixes with the iodine which already in the body. 24 hours later, the amount of iodine in the body which was taken up by the thyroid, is determined. A patient with a high hyperactive thyroid will have higher than normal level of RAIU, and vice versa. Another common method of radioactive in medicine is positron emission tomography, PET. PET is a imaging method that emits a positron. Medically, positron emitters, such as carbon-11, oxygen-15, and nitrogen-13, are used to diagnose conditions involving blood flow, metabolism, and brain function. Positrons emitted are detected by computerized equipment to create a 3D image of organ. Okay, as usual, at the end of chapter, we will see what are the connection of what we have learned today with our health and environment. Here, we emphasize on radiation and food. Do you know what is foodborne illness? Foodborne illnesses, caused by pathogenic bacteria, such as Salmonella, Listeria, and E. coli. For example, E. coli have been reported, by the Center for Disease Control and Prevention, to contaminate foods, that infects 20,000 people in USA only, and 500 people die. E. coli has been responsible for outbreaks of illness, from contaminated beef, fruits, and so on. So, FDA has approved the use of radiation, produced by cobalt-60 and cesium-137, for the treatment of foods. For example, gamma rays produced pass through the food and kill the bacteria. It is important for you to understand that radiation has no effect to the food, as well as heat. It is just used to stop the bacteria to grow. However, a small amount of vitamin B and C may be lost. Currently, most of fruits are being radiated when ripe, to extend their shelf life. The FDA has also approved the radiation of pork, poultry, and beef, to decrease infection, and to extend shelf life. Next, we will learn on the connection of radioactive with ancient objects. Radiological dating is used by geologists, archaeologists, and historians to determine the age of ancient objects. The common use radioactive for this purpose is carbon-14, which is used to calculate the amount of time has passed since the plant died. This process is called carbon dating. Carbon dioxide is continuously used by living plant during a photosynthesis. Some carbon-14 also will be taken into the plants. After the plant died, no more carbon-14 is taken up, the amount of it remained in the plant and decreases, as it undergoes beta decays. So, scientists use the carbon-14 to calculate the age of plant. The smaller the amount of carbon-14 remaining in the sample, the greater the number half-lives that have passed. Another application of radiological dating is to determine the age of rock, based on the splitting of uranium-238 to lead-206. The older rocks will have a high percentage of lead-206, because more of the uranium-238 has decayed. So from this, scientists can determine the age of the older rocks. As usual, to ensure you understand on what we are discussing today, let's do recapitulation. So, students should be able to explain on how does the natural radioactivity occur? Briefly explain on the medical applications using radioactivity. State one major characteristic of alpha particle, beta particle, and gamma ray. Now, we have reached towards the end of our lecture on this topic. Hope you enjoy watching the video. See you again next week. Bye.